So we talked about the autonomic nervous system in Chapter 9, and now we're going to backtrack to Chapter 6 and start talking about the somatosensory system, and then talk about pain and pain control in Chapter 7, and then we'll talk about pain matrix dysfunction, chronic pain, that sort of thing in Chapter 8. So there's a lot of information in Chapter 6. I'm going to try to break it up into sections so it is easy to digest. Don't get hung up on the names of things. We will go through that hopefully in a way that makes it understandable for you. So the somatosensory system, somatosensation itself is sensory information from the skin and musculoskeletal systems. So the autonomic nervous system is giving us using peripheral receptors to detect things like oxygen levels and chemical levels and pressure, from blood pressure and that sort of thing. The somatosensation is giving us some conscious sensory information. So it's giving us, and it's from the skin and musculoskeletal systems. So that being the difference between somatic and autonomic. So the information from the skin is superficial, like pain, touch, temperature, or cutaneous. Pressure and vibration is cutaneous, so deeper in the skin. Information from the musculoskeletal system includes information about proprioception and pain. So the information in the somatosensory system goes from a peripheral receptor through a series of neurons to the brain, and we're going to talk about that whole path. So really, the somatosensation is what allows us to interact with the outside world. It allows us to feel what's going on out there, to move accurately, to avoid or minimize injuries. So it keeps you from sticking your hand in the fire, or if you accidentally stick it in the fire, you take it out before there's any damage. So, of course, we have other special senses: smell, vision, hearing, our vestibular sense, and that sort of thing, but we will talk about those in other chapters. In this chapter, we're going to focus on the somatosensory system. So the superficial sensory information is pain, touch, and temperature, specific pressure and vibration. The musculoskeletal system tells us about proprioception and pain, and the stretch of muscles, tension on tendons, position of joints, and deep vibration. So proprioception includes both static joint position sense and kinesthetic sense, so sense of where we are in space. So last summer in 105, Lisa and Claudia talked to you a little bit about position sense and conscious proprioception. We also have some unconscious relay tracks which deal with proprioception and posture, and we'll talk about all of those. So really, somatosensation is necessary for living in the world, basically. So all of the pathways that provide us with information go via peripheral neuron axons. So the pathways that convey somatosensory information, they have an anatomical arrangement. So the peripheral axons that sense something going on in your leg are different from the ones that sense something going on in your arm or in your face. So we have that anatomical arrangement of information. So we talked about in chapters 2 and 3 that a threshold stimulus. So it's the same thing with somatosensory things. We have to have a sufficient stimulus to generate an action potential. So there might be something, if there's something lightly touching you, if it's not touching you enough for you to sense it, then it doesn't create a threshold stimulus, and it doesn't generate an action potential. So a little bit in chapter 4, when we talked about habituation, like getting used to the feel of a watch on your wrist or a ring on your finger or your clothing, you get habituated to that sensory information, and then you no longer generate an action potential. You're just used to it. It's habituation to that continued benign stimulus. So the thing that influences the speed of information processing, like how fast do we get that information from the periphery to the central nervous system, is the diameter of the axons, the degree of myelination, and the number of synapses in the pathway. So more synapses in the pathway, of course, is going to slow down the information. More myelination is going to speed it up. Larger diameter axons is also going to speed it up. So there is a distinction between sensory information and sensation. So sensory information is the nerve impulse that's generated from the original stimulus or stimuli. Sensation is the awareness of stimuli from the senses. So there has to be some processing involved in order to get to the step of sensation. So sensory receptors are, of course, the first step. So we're going to go through step by step. And we talked a little bit about this already in chapter 2, but sensory, and in chapter 9 as well. But sensory receptors are specialized to respond only to a specific type of stimulus. The stimulus has to be adequate to generate an action potential and under normal conditions. So you might. Have you ever had you come in from the outside and your hands are cold and you accidentally hit your hand on the edge of a doorway or sink and it hurts so much? So you have, that's not normal condition. That's not your normal response to just lightly bumping your hand on the door. But the conditions have been altered by something in the environment. So we'll talk about the different types of receptors, and these are the same types of receptors in the autonomic nervous system, but we process that information differently from the somatosensory system. So mechanoreceptors are touch, pressure, stretch, or vibration receptors, and they generate their action potential by a mechanical deformation of the receptor. Chemoreceptors are substances that they detect substances released by cells, including damaged cells after injury or infection. So remember from back in physiology or pathophysiology, where when cells are damaged, they release histamines and they release other substances to call other cells to the area, or to initiate an inflammatory response. So chemoreceptors are largely responsible for processing that information. Thermoreceptors, just like they sound, they transfer information regarding heat or cold. So there's a subset of somatosensory receptors that are called nociceptors. Nociceptors, a stimulation of nociceptors results in the sensation of pain. Like pressure mechanoreceptors, the example is you stub your toe. The sensation experienced is pain rather than pressure. So the nociceptors provide a little bit of information, but as we will talk about in the next couple chapters, whether it's perceived as pain or not gets decided in the brain. So nociceptors need a little bit more stimulus. So if there's a difference between something feels warm and something feels hot. Something feels warm, that's going to activate some thermoreceptors. Something feels hot, like it might cause tissue damage, that's going to stimulate the nociceptors. So nociceptors, you can kind of think of them as pain receptors, but what they really are is danger receptors. Nociceptors are saying, hey, there's something wrong. You have to take action to keep us from getting damaged, to keep your body from getting damaged. So they're damage receptors, they're threat receptors. So interestingly enough, you can have pain in the absence of nociceptive input. If your brain perceives danger, it can cause you pain, and that pain is going to cause you to take action of some sort. So very interesting, the idea of pain, and we will explore that even more fully. But the idea of pain in the absence of nociceptive input. So in the module, Oh, I brought this up, but it's coming up slowly this time. In the module, we have all this same information. We're going to start talking about steps in the sensation experience. So the first step in the sensation experience involves those sensory receptors that I just talked about. The sensory receptors are located at the distal ends of peripheral nerves, and they encode stimulation into receptor potentials. Peripheral axons they're afferent axons, so they take information from the periphery into the central nervous system, and they're classified by axon size. So the naming scheme is a little bit strange. We've talked about some of these, the A betas and the A deltas and the C fibers in last quarter in modalities class. We're going to add a few other axons to our vocabulary. So this chart is from the book, and it classifies axons by speed. So from largest, so we know a large, more myelinated axon sends signals faster than a smaller, less myelinated axon. The diameter of the axon is functionally important, meaning larger diameter axons transmit information faster, and larger diameter axons are more myelinated, allowing for saltatory conduction. So we'll talk about like less myelinated and more myelinated. There are very few peripheral axons in our body that are actually unmyelinated, even though we'll see that terminology used. You can think of it as more and less. So the more myelination, the faster it transmits the action. So there's a little video in the module about peripheral sensory neurons if you're interested. If you're not, please don't watch it. 51 seconds of your life right there. So then with the categories of sensory receptors that I just talked to you about, I have a lot of charts in this module because you know I love charts. And this is the information that I would like you to know for the exam. So what is the type of receptor, and what is the stimulus that activates that receptor? So this is the information that is encoded into the action potential. So mechanoreceptors, the stimulus is mechanical deformation of a receptor, so touch, pressure, stretch, or vibration. So some of those things can come from modalities that we do, like soft tissue mobilization. You can get touch, pressure, stretch, or vibration during soft tissue mobilization for the different techniques that we learned last quarter. Chemoreceptors respond to substances released by cells, and that includes the response to damaged cells following injury or infection. Thermoreceptors, of course, respond to heating or cooling, temperatures, and nociceptors are they're the subset that are sensitive to stimuli that damage or threaten to damage tissue. So you don't have to have actual damage in order to stimulate those nociceptors. When you stimulate the nociceptors, it results in a pain stimulus. The example of stubbing your toe stimulates pain from nociceptors rather than pressure from a lower threshold pressure receptor. The information might reach your awareness, but it is also used to make automatic adjustments like reflexes, withdrawing your limb from the danger. So know those different types of receptors and what their stimulus is. So the area of skin innervated by a single afferent neuron is called its receptive field. Receptive fields tend to be smaller distally and larger proximally. Distal regions have greater density of receptors than proximal. So think about it. If you were to stimulate sensory receptors on your hand versus sensory receptors on your low back or your knee, or something like that, the ones on the hand would be more sensitive because they have a greater density of receptors. So in this picture from the book, remember last summer in 105 when you were doing 2-point discrimination, you touched people with the calipers and you said, is it 1 point or 2 points? So here we have two sensory neurons, basically the yellow one and the blue one, we'll call it, and their receptive fields overlap a little bit. If you use the caliper A, both legs of the caliper A are in the receptive field of the blue neuron, and so that is going to be perceived as one point. Caliper B, one leg is in the receptive field of the blue neuron, the other leg is in the receptive field of the yellow neuron, and so that's going to be perceived as 2 points. So you can see how if there was a greater density of receptors and more overlapping receptive fields, you would be able to detect 2 points much more closely together. So in a more proximal region, they're larger receptive fields and not as dense, not as many of them. And so you're going to have the 2 points of the caliper pretty far apart to detect that it's 2 versus 1 points. In a more distal field, there are a lot of them and they're really close together, so you can have a pretty small distance between the two ends of those calipers and still detect it as 2 points. So it makes sense in your body, and that is the reason for it, because greater density of receptive fields and they are closer together. So there are also 2 types of receptors and how they respond. There are tonic receptors and phasic receptors. So tonic receptors are ones that respond as long as a stimulus is maintained. So an example of these is stretch receptors. Those, as long as you have stretch on the tissue, you are still going to get a stimulus. You're still going to get a response. Phasic receptors adapt to a constant stimulus and then stop responding, like I talked about with habituation. So the example is the brief response of cutaneous pressure receptors after putting on a watch. Eventually you get used to it. In a short amount of time, those receptors stop responding to the stimulus. So there's a 13-minute video about sensory receptors. It reiterates some of the information that I've already talked about. So you choose how you use your time, and if you have 13 minutes to spend on it and you want to, you can take a look at that video. So I'm really, as you've seen in this class, a lot of times I'll flip back and forth between the PowerPoint and the module, just because I think it's a useful way of presenting the information. So the peripheral sensory neurons have 2 axons. The distal one conducts messages from the receptor to the cell body, and the proximal one projects from the cell body into the spinal cord or brainstem. So these are those pseudo-unipolar cells that we talked about in Chapter 2. So the reason that it's classified as an axon versus a dendrite is the direction of information flow. So the axoplasmic transport, both legs of these somatosensory peripheral neurons are going away from the cell body. One of them is going from the receptor to the cell body, the other one is going from the cell body to the spinal cord or brainstem. So don't get hung up on the fact whether it's an axon or a dendrite, but it's just the flow of information basically is afferent from the peripheral to the central nervous system. Afferents are classified according to axon size. 1A is the biggest, 1B is the second. So 1A is muscle spindles, 1B is Golgi tendon organs, 2 A beta, A delta, or C. And we will go through all of those again. Larger diameter axons transmit information faster than smaller diameter axons. That's the same receptive field graphic that we just looked at. Receptive fields tend to be smaller distally and larger proximally. So we will wrap up this section, and in the next section we'll start talking about cutaneous innervation.